The Laplace transform method is a pretty handy method of solving a differential equation under the right circumstances. And what I find fascinating about it is that it's a way of turning a differential equation into an algebra equation. So we're essentially solving an algebra equation by using this method of Laplace transforms when we solve a differential equation. Now there's still calculus underpinning it all. The calculus doesn't quite go away, but it's a neat method that's been built up with tables of things you can look up and plug in. And so basically it does turn into pretty much an algebra problem when you apply Laplace transform to a differential equation. Now you might think, after you see one or two of them, think, well, sure, it's tedious. I can solve those equations quicker by other methods. And so we'll talk about when it may make sense to use Laplace transform over one of the other methods we've studied in this course. So anyway, let's start off by defining it. And I think his name was Simon Laplace, but he probably a Frenchman. I think he probably lived in the 1700s. I'd have to look that up. Could have been early 1800s. The Laplace transform, and I want to make sure I get it right, so I'm going to look at my book. And it's defined to be this way. L operating on f of x is equal to capital F of little s. I don't know if the s comes from Simon Laplace. I may find out if I look him up, maybe his name was something else. But anyway, that's kind of where I figured the s probably came from. And I lost my place here. Okay, here it is. It's an integral from 0 to infinity of e to the minus sx f of x dx. Right. Well, that's not intuitive at all, is it? I don't find it intuitive. But you have to bear with me as I develop this method. It'll start to make some sense once we get to apply it. But anyway, the Laplace transform uses an integration based upon the input value of f of x. And so the Laplace transform of f of x goes into here, f of x goes into here, multiplied by e to the minus sx, and you integrate from 0 to infinity. So it's an improper integral, which will almost always converge because e to the minus sx, whatever s is, e to the minus x gets small very quickly as x grows. And so whatever f of x is, this tends to overwhelm it and cause that product to go down to 0. In other words, whatever this looks like, it's integrable, generally integrable, because on the right hand side, as x goes to infinity, this just shrinks down to nothing quick enough in order for it to converge. Well, being that as it may, what are we going to get when we integrate this? When we integrate dx and plug in 0 to infinity, the x's are going to disappear, and what's going to be left is some expression using letter s, and we call that expression capital F of s. And so, for example, let's do some easy ones here. The Laplace transform of 1 is, well, f of x equals to 1, and so it's the integral from 0 to infinity of e to the minus sx dx. Okay, and that's not bad. We integrate this, and we get minus e to the negative sx over s, right? Yeah, if you take that derivative, the derivative is going to cancel the minus 1 over s. From 0 to infinity, and so now I'm going to abuse the notation here. It's going to be negative e to the minus infinity over s minus negative e to the 0 over s. Yeah, you're supposed to write this with limits and so forth, but as x goes to infinity, this goes to 0, doesn't it? e to the minus infinity just drops down to 0. So the first term is 0, and negatives cancel, e to the 0 is 1. This equals to 1 over s. Alright, so we have our first little formula here. Laplace transform of 1 is 1 over s. Okay, and you could say that's equal to capital F of s. I'm not sure how productive that is, but anyway, I'm sure that shows up in various notations. Alright, so Laplace transform of 1 is 1 over s. Let's do another one. Let's do the Laplace transform of x. Well, if I plug x into here, then I have x times e to the minus sx, and I reverse the order here for my convenience. Integral from 0 to infinity dx. And to do this, we've got to use the integration by parts strategy. So if I let u equal to x, dv equal to e to the negative sx, and then that makes du equal to dx, and v is minus e to the negative sx over s. I forgot to write my dx there, technically. So this equals to u times v, which would be minus x e to the negative sx over s from 0 to infinity. So it's u times v minus the integral of v du. So this is minus e to the negative sx over s dx. Oops, a little careless there. So u times v minus integral of v du from 0 to infinity. And those negatives cancel. Okay. So we end up with, what do we have here? If I plug in infinity, I better write that as a limit. So we have the limit as x goes to infinity of minus x e to the negative sx over s minus, plug in 0, and when I plug in 0 I have 0 times e to the 0 over s. That's just basically 0. And then we have this integral, and when I integrate this character, remember s is a constant here in the context of this integration, and so this will be a plus minus e to the negative sx over s squared from 0 to infinity. Alright, well, I need to make some room. I'll do a little erasing. This then equals to the limit as x goes to infinity, and what I'm going to do is change e to the minus sx into a denominator. So I have minus x over s e to the positive sx. And then over here we have minus e to the negative infinity over s squared again. And then plug in 0, subtract, plus e to the 0 over s squared. So what happens here? Well, this limit is, you plug infinity and you hit infinity over infinity. If you apply L'Hopital's rule, remember L'Hopital's rule says that when you have a limit that is indeterminate form, 0 over 0 or infinity over infinity, then, and this is minus infinity over infinity form, we can take the derivative of numerator and denominator separately and then reevaluate the limit. So that's just a reminder that sometimes we have to use L'Hopital's rule. So this limit, as x goes to infinity, I take the derivatives. It's minus 1 over s squared e to the sx. This is 0, because this basically, that limit goes to 0. E to the minus infinity just gets incredibly small over s squared. S, again, is a constant. Plus 1 over s squared. Okay, and now when we evaluate this limit, this goes to infinity, the denominator goes to infinity, the numerator is constant, so the fractions get smaller, this just goes to 0. So now we have two Laplace transform formulas. First of all, we figured out that Laplace transform of 1 was equal to, what was it? I think it was S, wasn't it? No, it was 1 over S. Now I'm doing it from memory. The Laplace transform of x is equal to 1 over S squared. All right, well, let's don't do any more of those. Because the good news is that the big ones have been worked out. And they're in your book. And if you don't have this book, I'm sure it's in a different book you're using. If you're doing Laplace transforms. Now, in this book, you'll find a table on page 306. And so, it's called the short table of Laplace transforms. The first line is if f of x equals to k, then Laplace transform of k is k over s. So it turns out that you could replace this with a different constant, it just multiplies. And then the Laplace transform of x to the first power, this will be the second line, x to the n, is n factorial over s to the n plus 1. If you plug 1 in, you'll get 1 over s squared. And anyway, there's a bunch of those on there. Let me write a few of these on the board. I wrote a few of these Laplace transforms from the table on page 306. And Laplace transform of a constant k is k over s, where s is greater than 0. The authors are very rigorous about their work, so they have to specify some certain things that make this work. Laplace transform of a power of x, x to the n power, where n is a positive integer, would be n factorial over s to the n plus 1. So this would not work for a square root, because then n would be 1/2. It would not be an integer, so that would be another issue to deal with. Laplace transform of e to the ax happens to be 1 over s minus a. Very short and sweet. And then for the sine function, sine ax, the Laplace transform happens to be a over s squared plus a squared. So of course there are more of them in that table, and there are probably some sources that have yet more of these Laplace transforms, and that you could look up as a reference. So it doesn't begin to remove the mystery as why are we doing this? And so have to bear with me. I'm going to erase the board and then tell you some more about how these are used. Well, our first issue that's nice to know about the Laplace transform is that it's a linear operator. And a test for linear operator is this. Does the Laplace transform of c1f1 plus c2f2, where the c's are constants and the f's are functions, does it equal to a constant times Laplace transform f1 plus c2 constant lf2? And it does. And for a very simple reason, this is a big integration, and you can factor the constants out of the integration, and if you're integrating a sum, you can break it up into two separate integrals. And so this makes Laplace transform a linear operator. Okay, well that's good to know. We have a little experience with linear operators, and that's a nice feature. Okay, next problem is what is the Laplace transform of y? Well, it's an integration. It's the integral from 0 to infinity of y e to the minus sx dx. Let me make sure I got this down. I'm pretty sure I do, but I don't want to mess up this video. Yeah, okay, that's correct. All right, just making sure here. Okay. Now, if that's the case, then what's the Laplace transform on? Oh, there goes my book. On y prime. Okay. Well, Laplace transform on y prime would be the integral from 0 to infinity y prime e to the minus sx dx. Okay. Now, I'm going to see if I can figure out how to express L of y prime in terms of L of y. And so I'm going to start by solving this integration by parts, integration by parts. So I'm going to let u equal to e to the minus sx, and dv will equal to y prime dx. So that makes du equal to minus s e to the minus x, and it makes v equal to, well, v will be the integration of y prime dx, just simply y. So when I plug this in using the integration by parts, I have u times v, so it'd be e to the minus sx times y, evaluated from 0 to infinity, and then minus the integral of v du, so this would be minus s y e to the negative sx dx. And I forgot to write my dx there, sorry about that. So here is u times v minus integral of v du. Well, let's see. That negative cancels, that's the easy part. Over here, we have basically e to the, well, I'll write it out the way you're supposed to. This would be limit as x goes to infinity of e to the minus sxy minus, and I'll plug 0 in. When I plug in 0, I get e to the 0 times y at 0. And then on the right side, I have plus s integral y e to the minus sx dx. And again, that's going from 0 to infinity. Okay, well, let's look at this. We're going to make an assumption that this limit goes to 0. And if it doesn't, there are very few functions that overpower e to the minus sx. And so there's probably some rigorousness here I need to investigate. But basically, for when we can apply Laplace transform, this has to be 0. And e to the 0 is 1. So we end up with what? You see, this is minus y at 0. And then, if you look carefully here, this is s times Laplace transform of y. This is s Laplace transform of y. So what I just derived was this. I need to erase, and I'll write down what I just derived. So what we just derived was the Laplace transform of y prime is equal to s times the Laplace transform of y minus y at 0. Now y at 0 is an initial condition. So beginning to see that if we're going to make any use of this in solving differential equations, we need initial conditions to solve it. So that's going to end up being pretty important there. Okay, let's go ahead while we're at it. Let's see if we can figure out what L of y double prime is. Okay, well, this is the derivative of the derivative, so this would be SL of y prime minus y prime at 0. So I just substituted the derivative of y into here, and then we have this expression, L of y prime, so this would be this s times this expression for L y prime, S L y minus y at 0 minus y prime at 0. And now we can write out L y double prime. So L y double prime is going to be, what? It's going to be s squared L of y. Oops. Alright, so s squared L operating on y minus s y at 0 minus y prime at 0. There we go. So there's Ly double prime. So you're starting to see the derivatives appear, and now we're about to apply this to a differential equation. And but we needed to figure out how to handle the Laplace transforms of derivatives. And now we could come up with, if you needed it, to solve a third order differential equation with Laplace transforms, you could use the same idea and piggyback on it. So you would use Ly double prime, replacing these with y primes. So this would be s squared Ly prime minus s y prime is 0 minus s minus y double prime is 0. And then you get to reinsert this, and anyway, just kind of go through the same process. It's more tedious, and you can keep generating these formulas for Laplace transforms of higher order derivatives. So that's a possibility. Okay, well, now I think it's time to see how this works when working problems.